Part A, Miss Marple wanted to find the hotel with the shortest number of maximum number of shortest paths. In this, she wanted to find the safest hotel as the one that had the highest number of shortest paths from the train station. The idea is if she can reach it in multiple shortest way, it's less likely she'll get lost. Since the graph unit has distances, I used BFS, breadth first search. It always explores the shortest path first in unweighted graphs. I also counted the number of ways to reach each node at the shortest distance. If a node can be found again with the same minimum distance, I will increase the path count. This helps us track all the possible number of shortest paths. This method runs in O n plus m count, which is the runtime complexity of this task. Part B, the testing connectivity of the network. This part checks if the given directed graph is connected, meaning there's a path between every pair of nodes. In this, I also used BFS. We started from one node, marking it as visited, and I keep exploring the neighbors. I maintain a visited array, and at the end, I check if all the nodes were visited or not. If even one node is not marked as visited, the graph is not connected. This works well because in BFS, we explore the entire component of the start node, so we only visit some nodes and not all. That means the graph is not fully connected. Again, this also runs in O n plus m complexity, which is optimal for adjacency lists. This kind of check is useful in real-time networks like the internet to ensure all the devices or computer can talk with each other. Part C, runtime of DFS using adjacency metrics. Now let's say we wanted to run DFS, but the graph is stored as an adjacency matrix instead of a list. Here, if a node has only few edges, we still have to scan the entire row to find them. That's O n per node, and there are n number of nodes, so the total time becomes O n square, even if the graph only has a few edges. This is much slower than O n plus m, which we get in the adjacency list, especially in sparse graphs. Part D, the algorithm. In these, we have to explain some iterations. I'll be explaining 3. This finds the shortest path from a source node to all others as long as the edge weights are non-negative. We use a priority queue to always pick the node with the smallest current distance. Then we relax its neighbors by checking if going through this node offers the shortest path. Here, I will be explaining 3 iterations. Iteration number 1 will be starting at node 1, and we will be checking the neighbors. The distance will be 0, and then we'll visit node 2, and the distance will be 3. We'll update that. Then we will visit the node 6. The distance will be 10. We'll update that, and then we will add node 2 and 6 to the list as queue in the queue, and mark node 1 as visited. Next, closest is node 2, which has the distance 3. Then we'll check the node 4 neighbor, which are the neighbors of the node, and the new distance will be 8. The old distance is 5. Then the updated distance will be 8 because the 1 to 2 has 3. Then node 5, which has the distance 11. Node 7, which has the distance 7. Node 8, which has the distance 1. And we will update all of these as we will update node 2 as visited. Then we will for the iteration 3, we'll check the node 8, which has a distance 4, because as 1 is there and 3 was the old distance, so 4. And after that, we'll check the neighbor node, which is 3. And sorry. Then next closer node is node 8. This is the iteration 3. Next closer node is node 8. We'll check the neighbor node, which is 3, and the distance will become 14. As node 3 to the queue, mark node 8 as visited. And after 3 iterations, we have finalized 1, 2, and 8. And we'll do this for the rest of the iterations until we have all of the nodes which have been visited, and we will find the shortest distance calculated. This was the algorithm. Then we'll go with the part E. If every edge weight is decreased by one, is increased by one, let's say we have a path with two edges and another with three edges. At first, the longer path might be shorter in total weight, but if every edge weight increases by one, the longer path gets penalized more. For example, path A had two edges, path B had three edges, but if every edge goes up by one, the result of path A will be 2W plus 2, and result of path B will be 3W plus 3. So the shorter path now may become cheaper. This proves that increasing all weights by 11 can change the shortest path, especially when the lengths are different. To summarize, I think I have applied BFS for all of the shortest paths and connectivity, and discussed the performance of the DFS with different graph representations. And here I conclude my video for the assignment 8.1. I hope I have covered all of the topics. Thank you.